This is the solution for Chapter 12, Video Assignment 1. The question reads, at elevated temperatures, a nitric dioxide reacts with carbon monoxide, producing carbon dioxide and nitric monoxide. There are two proposed mechanisms for this reaction. In one possible mechanism, products form directly from a bimolecular collision that directly transfers an oxygen atom from NO2 to CO. In another possible mechanism, two nitrogen dioxide molecules collide in a rate-determining step to form NO and NO3. A second, a much faster step, has a nitrogen trioxide molecule collide with carbon monoxide to form nitrogen dioxide and carbon dioxide. So first we need to determine the rate law for each of these proposed mechanisms. So the first mechanism here is really straightforward. Just NO2 combines with CO. They hit it just the right orientation, and an oxygen atom pops off of the nitrogen dioxide and pops onto the carbon monoxide, forming carbon dioxide. So for the rate law we can write for this, it's really straightforward. It's a bimolecular collision, so a CO is going to hit an NO2, so really the rate of reaction is determined first order to CO and first order to NO2, right? Because if you increase one of them, they're going to collide more, it'll increase it just by the same amount. So for this mechanism, we can write the rate law as rate equals the rate constant times concentration of carbon monoxide times concentration of nitrogen dioxide, because it's just a simple bimolecular collision. So similar over here, we've got the mechanism written out. Two NO2s collide, an oxygen pops off to form an NO3 and an NO. This is the rate determining step, so this is slow. And then a much faster step following this NO3 hits a CO to form NO2 and CO2. Now to just verify that this reaction works, we can cross off stuff here, leaving us with NO2 plus CO reacts to NO and CO2, which is what we're looking for. So if this is the rate determining step, then we can write the rate law. It's just another bimolecular reaction, except this time it's an NO2 hitting another NO2. So the rate law equals the rate constant times concentration of NO2 times concentration of NO2, right? Since two of them have to hit. So it can also just be written as rate constant times NO2 to the second power. So in this one, it's second order in relation to NO2 and 0th order in relation to CO, because it's not really relevant how much carbon monoxide is there, because that step is really fast. This is the slow step, this is the one that we care about. So now that we've determined some theoretical rate laws, we have to experimentally determine which one is correct, which mechanism of reaction. So kind of I guess I'll stay this way. The experiment that I thought up is to have a box right here with two compartments with a door, a hatch, a slide, something separating them, right? And so on the one side, we'll assume that we can suck the air and make them both vacuums. On the one side, we'll fill this side with some concentration of nitric dioxide, and this side with some concentration of carbon monoxide. And I just drew a table with the different molarities that we can do. First we'll have 0.1 molar NO2, 0.1 molar CO, and we'll just keep these, as you can see here, keep it consistent for the first three trials, and increase this one, incrementally, the first two trials, and then keep these ones consistent for these trials, and increase these ones. So we'll talk about that in a second, but how the reaction, or the experiment will work is we'll put in your desired molarity of gas in each side, and the way that we'll measure how we'll measure the molarity in each side is I got a pressure gauge here, and if we rearrange the gas law, universal gas law, moles divided by volume, we'll know the volume of the container, right? So we'll know the volume, we'll know the pressure, we'll know the temperature. I just said we'll go 300 degrees Celsius, because the question states at elevated temperatures, and that's pretty elevated. So, so we know R, obviously universal gas constant, we know T, which we'll do in Kelvin, we know the pressure, and we know the volume. So by using all these, by dividing the pressure by R and the temperature, we can determine what the molarity is in each side. So that's how we'll regulate, that's how we'll decide what the molarity is for the gas in each side, is by using this pressure gauge and temperature being consistent and knowing R. So anyways, point is we'll put the different molarities of the gases on either side, and then when we're ready to perform the reaction, we'll open the hatch or lift it up or however it works so that the gases can mix. Now, as they mix, obviously one of the products is CO2. And I just did a little handy Google search. I said, is there a way to measure CO2 gas in a solution? And the answer is yes. So you use what's it called? A non-dispersive infrared sensor. I don't know exactly how it works, but the point is you shine infrared light through the gas and measure it on this side how much CO2 is there. So we'll hook that little thing up there too. As the reaction happens, we'll measure the rate of CO2 over time, get the data, and so we'll get an initial rate. So we'll do this reaction 5 times with the different concentrations of each, get the initial rates, and then we can look at them and see what's up. So for the first ones, the 0.1 molar nitric dioxide and the 0.1 molar carbon monoxide is kind of just a baseline to give us something to go off of. So in the first couple trials, we'll leave the nitric dioxide steady and we'll increase the molarity of the carbon monoxide. Now, when we do this, if we see no change in the initial rates between these 3 trials, then we can assume that this is the mechanism of action, right? Because carbon monoxide is 0th order in this mechanism. So if changing the molarities of carbon monoxide in the reaction doesn't do anything to the rate, then we can assume, we'll fail to disprove, I guess, that this is the mechanism of action. Now, if we see the initial rate increasing as we increase the molarity of carbon monoxide, then we can assume that this here is the mechanism of action. And this one, same goes for here. We'll leave the carbon monoxide steady. If we increase the nitric dioxide, in both mechanisms, we should expect to see the rate increase, but the rate is going to increase by a greater magnitude when you increase the molarity of nitric dioxide for this reaction, right? Because this is second order, so if we double the molarity, we should expect to see the rate quadruple. But if the rate just doubles, then we can assume it's this mechanism. Now, one little caveat just at the end, when we open up the hatch and mix the gases, the molarity will change because you have the same moles of gas, but the volume of the container is bigger. So when you do like the actual data analysis, you will, I don't know, whoever does the experiment, will have to just use this proportionality to get accurate values. And I'll just draw it out real quick. Let's just say that this is 2.5 liter, or let's say it's 1 liter, and then 2 liters together. So, right, the molarity of nitric dioxide is 0.10 at 1 liter, but we now make it 2 liters, so you got to times across and divide. So, that's how you're going to determine the new concentration for all of the gases. That way, when you actually do the data analysis, you can see the proportions. Okay, is it doubling, is it quadrupling, so on and so forth. So, in summary, using this little apparatus, we can mix the nitrogen dioxide and carbon monoxide at different concentrations and measure the CO2 produced based on the results. If carbon monoxide changing in concentration changes the rate, then we can know, we can assume, we can make our hypothesis, our theory, that this is the mechanism of action. If carbon monoxide, did I say doesn't? Okay, I'll restate it. If changing the concentration of carbon monoxide does not change the rate, then we can assume that this is the mechanism of action. If changing the concentration of carbon monoxide does increase the rate, then we can assume that this is the reaction mechanism.